So this is part 2 of saying gravity is not a force, is nonsense. So I'm dealing with a video by a physicist called Sabine, and she was talking nonsense, saying gravity was not a force, and I pointed out other sources that were saying that gravity was a force. And so based on that nonsense of believing gravity was not a force, she then proceeds to pile on more nonsense in an attempt to get other issues to tie in with her false claim. So I'm continuing with her video.
Gravity is not a force.
Throughout her video, she keeps saying gravity is not a force, that is nonsense, and she fails to properly explain why others say it is a force. Although it makes an attempt, it is an inadequate attempt. As pointed out in part 1, Kip Thorne points out space-time curvature and tidal gravity must be precisely the same thing expressed in different languages. So the issue becomes, how does Sabine interpret something like that? It should be interpreted as space-time curvature is in Newtonian physics force. Sabine was talking about other forces than gravity. Just when she gets to gravity, does not want to talk about it as a force. When talking about forces, then in Newtonian context, should be saying gravity is also a force. Thus, she is wrong to say gravity is not a force because in Newtonian context it is a force. So, recapping, Sabine does not seem to understand things like space-time curvature and tidal gravity must be precisely the same thing expressed in different languages. Instead, she seems to be thinking space-time curvature and tidal gravity forces are different things. That makes a confusing mess of things. We do not see space-time curvature with our eyes, i.e. we do not see in four-dimensional space-time. What we see is in 3 dimensions of space, and for that we interpret in terms of forces usually. Thus there is a mapping from the mathematics of space-time to the 3 dimensions we observe in terms of forces.
And since there's no force pushing down on you, that means you're currently accelerating upwards. Unless you're watching this from the ISS, in which case, please say hi to the moon.
So, if standing on the Earth, she says there's no force of gravity pushing you down, so are accelerating upwards, and that's just more nonsense. The way to think of the accelerating upwards in the Newtonian context is to think of it as a force. Thus, if you're standing stationary on the Earth, the force upwards has to be balanced by a force pushing you down, which is gravity, to stop you flying off. Her point of view is that there is no force of gravity. Have to now look into that as she continues.
How does gravity work if it's not a force? That's what we'll talk about today.
And so on, we have to look into that.
An accelerometer is a device that measures acceleration. If you'd hold an accelerometer steadily in your hand, it'd tell you it's accelerated upwards. This isn't hypothetical, weird, theoretical physics talk. You can buy one and just see what it says. This is an example of how the reading of an accelerometer looks like when it's lying still on a table. It tells you it's accelerated upwards. And this is entirely correct. If you hold an accelerometer still on the surface of Earth, It's indeed accelerated upward. Why does that surprise you? If you hold something on your hand, you feel that it's pressing against your hand downward. It's like when you're trying to accelerate a car with your hand, it'll push against it.
So the groan is she doesn't understand about accelerometers. So this is from Dimension Engineering, and it explains about accelerometers, and it's still dealing with forces. In particular, it mentions acceleration forces and mentions force of gravity. So accelerometer deals with gravitational forces and other forces. She seems to forget Newton's third law, which can roughly be stated: to every force there is an equal and opposite reactive force. So there's a force upwards balanced by gravitational force downwards if stationary on surface of Earth. Trying now to be fair to Sabine, from her point of view, she's interpreting gravity as not a force, and so now interpreting accelerometers as not dealing with gravitational force, which would then be contrary to the technical specifications that I've just given. Ideally, she should be pointing out that her point of view is now interpreting everything differently to how normally understood, but of course she's not doing that. So anyway, proceeding onwards.
If you hold something in your hand, that's not the gravitational force pushing it down, because gravity isn't a force. It's pushing on your hand because you are accelerating it upward.
Pushing upwards is against gravity, but she is continuing to deny gravity is a force, so making a mockery of Newton's law that there is a reactive force to any force.
Why is the thing in your hand accelerated if you don't move your hand? It's because you are accelerated, and you are accelerated because there's a force pushing on you from below. That's the floor, or rather the atomic bonds in the floor and in the ground below.
Yes, force from the floor is from its atoms, and that's upwards, and force from gravity is downwards, but once again she is denying the gravity force.
You see, the entire Earth has internal pressure, otherwise it'd collapse. That pressure generates a force on everything on the surface, and as Newton taught us, a force creates acceleration.
Sabine is saying about force creates acceleration, and that's in the Newtonian context. The fact that she seems to forget when it suits her about gravity, because gravity creates acceleration and therefore should also be a force.
So that pressure of Earth creates a force which accelerates you on the surface. But wait, you may say, there's also the gravitational force pushing down.
Yes, she's finally talks to the gravitational force pushing down.
So the two forces balance to zero, right?
Yes, two forces approximately balancing. Unfortunately, Sabine is going to say it's not like that.
No, because gravity is not a force. Gravity is a consequence of moving in a space-time that's been curved by the presence of masses.
So Sabine is back to saying gravity is not a force. It says gravity is a consequence of moving in a space-time that's been curved by the presence of matter. So back to what Kip Thorne points out, space-time curvature and tidal gravity must be precisely the same thing expressed in different languages. It should be interpreted as space-time curvature is a Newtonian physics force. Sabrine not wanting to talk about it that way makes a mess. When talking about forces, then in Newtonian context, gravity is also a force. Thus she is wrong to say gravity is not a force, because in Newtonian context it is a force. Sabine's point of view seems to be some acceleration is due to force and some acceleration due to space-time curvature, which is nonsense in the sense, if you want to deal with Newtonian physics, then have to stick to talking about it all in terms of forces. Can't mix in part forces and part space-time curvature. If wanting to deal with general relativity, then description in that is space-time curvature, and not mix it in with how Newton deals with it as forces. Kip Thorne points out is two different languages, and Sabine is just mixing up languages, trying to mix in part of one language with part of another language, and that's making a mess. Have to go back to basics in gravity theory. In context of Newtonian physics, now it's best to go into detail about uniform gravitational field and non-uniform gravitational field. Give uniform and non-uniform gravitational forces. Putting aside the issue that stretching of the falling object can occur caused by gravitational force for the moment, the first picture we show there is uniform gravitational forces. Object falls along these parallel lines. So if you put dropping two objects in a uniform gravitational field, those two objects will fall in parallel lines. Now that is for when the Earth is considered to be flat. Actually the Earth is not flat, so what you have is a non-uniform gravitational forces from non-uniform gravitational fields, and objects don't fall along parallel lines. Now this is still in the Newtonian context. So for the Earth as approximately a sphere, lines of the gravitational forces point to the center of gravity of the Earth. So if you're on the Earth, you drop two objects, those objects will want to fall towards the center of the Earth, and what stops them getting to the center of the Earth is they will hit the ground eventually. But on those, the paths they take are in non-uniform gravitational fields, and that means they're not falling along parallel lines. The objects, as they fall, they get closer together, and this is ignoring any gravitational attraction between the objects as they're falling. And when it is non-uniform gravitational field, then it's called tidal force, and that's when the two objects as they're falling are getting closer together. They're not falling along parallel lines, they're falling and they're getting closer together. And the effect is very small for the Earth, of course, in normal circumstances. And I think it needs explicitly stating as non-uniform tidal gravitational force and uniform non-tidal gravitational force. And so we have both types of forces as part of Newtonian tidal gravity theory. When people talk gravitational force, they often mean uniform non-tidal gravitational force. And forget there is also a non-uniform tidal gravitational force. The emphasis is not being made that there are two types of gravitational force, and that can cause confusion. Next. So this article is Physics Bootcamp, and it explains tidal forces in more detail. And it says, when a body is subjected to a non-uniform force, different parts of the body experience different forces and consequently accelerate to different extent. And so body will deform as shown in the diagram there, which is called figure 12.91. As an object falls under Earth's gravity, then there is a stretching of that object because gravitational field is non-uniform. That stretching is not very much, so for most purposes can ignore it. However, in a strong gravitational field, such as a black hole, then that stretching is big, and it's called spaghettification. Here's a picture of a astronaut falling into a black hole, or what's a pictorial representation of that, and the astronaut is being stretched by the gravitational forces of that black hole. Notice I say gravitational forces, and that's the astronaut is stretched, and it's called spaghettification. Sabine seems totally unaware of the complications of dealing with gravitational force, and when she talks of gravitational force, she seems to mean uniform non-tidal gravitational force, and seems to forget there is also a non-uniform tidal gravitational force. She has the image of the gravitational forces pointing towards the centre of gravity of the Earth, so she should be talking about tidal force, but she doesn't mention it. Once again, she's glossing over things. It's sort of like should be vitally important to talk about tidal forces, but because she's got a picture where you could see the tidal forces, but she doesn't mention it.
If there are no masses nearby to curve spacetime, it's flat.
So Sabine tells us that if there's no masses to curve spacetime, then it is flat. But that is problematic. They, which are the mainstream, often talk of an object in special relativity contexts as having mass. So they, mainstream, must mean treating it as flat as an approximation. But Sabine not saying that's what they are doing, i.e. not saying what the mainstream are doing. Thus, yet another example of something she is not saying, which if she said would clarify things. Sabine suffers a lot from not saying certain things. In flat spacetime must be able to deal with uniform gravitational field. When gravitational field is non-uniform, then they find the need to curve spacetime, they being the mainstream. Flat spacetime is special relativity, where not flat need to go to general relativity. The curving of spacetime is the tidal force, i.e. the non-uniform force. You can get away with the uniform force in special relativity contexts. And here's a picture for it. When I have flat space-time, it looks like this. This is the earlier which showed you for the uniform gravitational field. And when it's non-flat space-time, it can look like this, and that's the non-uniform field. This is the reminder, putting aside the issue, that stretching of the falling object can occur caused by gravitational force. Uniform gravitational forces, objects fall along this parallel lines. Earth is not actually flat, so non-uniform gravitational forces and objects don't fall along parallel lines. For Earth as approximately a sphere, lines of the gravitational forces point to the centre of gravity of the Earth. And if there is a gravitational force in flat space-time, then is uniform gravitational field. When have a non-uniform gravitational field, then gravitational force in that is called tidal force. Pointing out again, uniform gravitational force in uniform gravitational field, non-uniform gravitational force in non-uniform gravitational field called tidal force. Taking Sabrina's example, mainstream does not usually seem to adequately explain that there is a difference between uniform gravitational force and non-uniform gravitational force. There are other problems to consider with this description presented here. If have masses in a flat space-time, then those masses will tend to attract, and then the lines will stop being parallel. But as I pointed out, presumably they are treating it as approximately flat. Thus, flat space-time tends to be an approximation when dealing with objects, because the objects will start to make the space-time non-flat. These lines are trajectories of bodies showing direction of motion and hence a force, but in general relativity treating as geometry of space-time. Anyway, back to Sabine.
So long as there's no force acting on an object in this flat space-time, the object will move in a straight line.
So what's Sabrina saying? So long as there's no force acting on the object in this flat space-time, the object will move in a straight line. But there are forces, so must mean an approximation. However, once again, not saying that. There are lots of things she should be saying, but is not saying, and is creating an ongoing bigger mess.
If there are masses nearby, space-time will curve, and the object no longer moves in a straight line.
So Sabrina is saying now, if there are masses nearby, space-time will curve, and the object no longer move on a straight line. And as pointed out, she needs to talk in terms of approximation, but it's not doing that. Should be saying something like space-time curved by mass, but if not very strong, then approximate by flat space-time, or something like that, but she's not saying it.
Even in the absence of a force.
Sabine says, even in the absence of force. Need to tie that into what I said earlier. So the complete sentence is, if there are masses nearby, space-time will curve and the object no longer move on a straight line, even in the absence of a force. So Sabrina totally messes up, as I've now explained. Unfortunately, she just carries on, and then thus I need another video. So to be continued.